So this is going to be video 2 for section 2.2. And we have a theorem here. I'm going to give this theorem a title. I'm going to call it the matrix vector equation AX equals B has a unique solution when A is invertible. Now, what does this theorem say exactly? Let me write out the details. It says if a matrix A is an n by n invertible matrix, so if matrix A is an n by n invertible matrix, then the matrix vector equation, AX equals B, that's also considered a linear system, right? You can write a linear system in that form. So this linear system, AX equals B, has a unique solution, for each vector B in Rn. Namely, the solution is going to be A inverse times B. Your solution X is going to be A inverse times B. Now let's go ahead and prove this. See if we can prove this. If I wanted to prove an if-then statement, I'm going to assume this part here right after the if. So we're going to assume that. So suppose A is an n by n invertible matrix. Suppose A is an n by n invertible matrix. So we start with that, and we're going to work our way to trying to show that AX equals B has a unique solution for every B in Rn. In particular, the solution is going to be X equals A inverse B. So first, we have to show that there exists a solution. So first, we're going to show that AX equals B has a solution. That's the first step. All right, so first, we show AX equals B has a solution. So first we're going to show there is a solution, then we're going to show it's unique. Unique means only one. So starting with the has a solution. So let's try plugging in something for X. What do we say X should be? Well, we're told here that X should be A inverse B. Let's try plugging in A inverse B in place of X. So let's take A blank. So in place of the blank where the X would be, I'm going to put A inverse B. That didn't show up too well. Let's try to squeeze that in a little better. Okay. A inverse times vector B. So we know we have an associative property. We proved that a while back for matrices and matrix vector multiplication. So you can reassociate the A with the A inverse, like so. And then you have vector B here on the end. We know A inverse times A, or A times A inverse here, this right here. We know that's the identity matrix, the n by n identity matrix times vector B. And we know that the identity matrix times vector B is vector B. So notice back here, we plugged in A inverse B, and over here we have the output is B, right? So we have A times that yellow gives us the B. So that means thus X equals A inverse B is a solution. Is a solution to the equation A times X equals B. Right? Because A inverse B can take the place of the unknown X, and your output is B. All right, so we've shown that there is a solution. Let's show that this solution is unique. And that means it's the only solution. So we show x equals A inverse B is the only one. All right, let's see. I'll scroll a little bit. No, that didn't work, did it? Okay, let's try scrolling again. So from the first part, we know there is a solution, right? We know there is a solution, A inverse B. We don't know how many solutions there are. We want to show that there's only one, but at this point, we haven't been able to show that. So let's pretend we have as many solutions as we want. So let's say, let U be any solution. So let's let X equal U be any solution to the equation A times X equals B. So let X equals U be any solution. So that means in place of that X, that yellow X, so yellow X is an unknown, I'm going to plug in U for X. So I'm going to have A times, instead of X, I'm going to have U, right? U is any solution. And that's going to be equal to the output B. Now what I'm going to do, I'm going to hit both sides of that equation coming from the left by A inverse. So I'm going to multiply on the left by A inverse. I'm going to have A inverse times AU. Oops, that should have been yellow. Oops. And A inverse times B. So we just hit both sides of that equation coming from the left. So we can reassociate the A inverse and the A together using our properties. Then you have A inverse A times U. That's equal to A inverse B. Now what is A inverse A? A inverse A is going to be the identity matrix times vector U. That's equal to A inverse B. We know the identity times vector U is vector U. That's A inverse B. Now remember what U is, right? U back here, X equals U, that's any solution. So what we're saying is any solution is forced to be A inverse B. So thus, the only solution is X equals U, which was A inverse B. That's it. That's the proof. So we've proven that's the only solution when you have an invertible matrix. Okay, so let's actually make use of this theorem. Let's do an exercise. Solve the linear system using the inverse of the coefficient matrix A. Okay, so here's a little exercise. Let's say I have a linear system. Let's call it 2x1 plus, let me think here. Let's say 5x2 equals, let me think here, 1x1. Let's do plus 3x2 equals, let's say, -2. and let's say -3. So we want to solve that linear system. Now we have lots of techniques for solving linear systems, but we're going to use the method where we find the inverse of the coefficient matrix. So I mean, if we want to set this up in AX equals B form, right? AX equals B form, your matrix A would consist of the coefficients 2, 1, 5, and 3. And your vector X would consist of the vector with entries x1, x2. And your vector B would consist of -3 and -2. That's the right-hand side of your equation. So what I'm going to do, I am going to write down A here, right as 2, 1, 5, 3. And I'm going to find A inverse. How do you find A inverse? Well, remember, you take 1 over the determinant. So you're going to have 1 over, what's the determinant? 2 times 3, 6, minus 5 times 1, 5, multiplied by, so what do you do with the 2 and the 3? The 2 and the 3, you swap those out. So you're going to have a 3 up in the upper left and a 2 in the bottom right. And what do you do with the 1 and the 5? You flip the sign, so you get -1 and -5. Right? So what's A inverse? So I'm going to have what? 1 over, what's 6 minus 5? Well, that's going to be 1, right? So we're going to have 1 over 1, which is just going to be 1, times 3, -1, -5, and 2. So when you simplify A inverse, that didn't work out too well. That was supposed to scroll. When you simplify A inverse, you're simply going to get what? 3, -1, -5, 2. So there's A inverse. So if I wanted to find the solution, X, put that in green, I guess. We know that since A is invertible, right, there is an inverse, we know that the solution to this is going to be A inverse times B. In other words, x1, x2, that solution vector, is going to be your inverse matrix, which was, let me scroll this a little bit. Your inverse matrix is this guy. 3, -1, -5, 2, times your vector B. What was your vector B? It was -3, -2. So let's go ahead and multiply that matrix times that blue vector. Red matrix times the blue vector. How does that work? We're going to take -3 times the first column, 3, -1. Right, it was this entry times the first column. And then plus the next entry, -2, times the second column. And that'll give you your solution, x1, x2. See if we can scroll. Yep, it's scrolling. So if I do that, I'm going to get what? -9 plus 10 for the first entry, and 3 minus 4 for the second entry. In other words, x1, x2, your solution is 1, -1. That's your solution. 1, -1. So x1 is 1, x2 is -1. You can go back and check that out, the original equation. Let's see. If I plug in 1 here for x1 and -1 here for x2, yeah, that's going to give me -3. I plug in 1 here for x1 and -1 here for x2.